Hello everyone. Today we try to learn some sorting algorithms, and for our course we need to understand how it works, and you will see some basic algorithms like classic ones, and our goal for today not to review all of those algorithms, only I picked the random three because those algorithms maybe it's more interesting than another when you have the same idea like comparing elements and have a bit different order to compare these elements. And I pick really separate styles like to merge sort, radix sort, and bubble sort. Bubble sort is like classic algorithm. It's not very effective, but we need to see how it works. And for our algorithms, of course, we learn the array sorting algorithms. And in this course, you're able to sorting, of course, more than arrays. If you have different like linked lists, list trees, etc., you're able to sort using different data structure. But for basic understanding, you must learn first using the array sorting algorithms, then you're able to move into other data structures. And of course, in the array, you're able to write and tree data structure also, if you would like to do this. It's not a big deal to make like to add the tree data structure into the array. But of course, it's more better to create your own structure or struct, and you just able to use any sort algorithm to sort the elements. And when we look in this sheet, and you see the algorithm name, time complexity and space complexity. And when you have small data sets or small collections of data, you doesn't care which algorithm you pick, it's work like a charm and it's working good. Maybe you need to look into the space complexity if you need to not waste the memory. But of course, the algorithm complexity always will be for the huge data sets when you have the n elements. And for the worst case, it's the best decision pick from average or worst case, because you know the real algorithm working, how much it takes in our case. And as you see, quick sort it's n log n, merge sort, tim sort, heap sort, bubble sort, and is red color it's not so good. Green is the best, yellow it's middle, orange it's fair, and of course sometimes if you have small data sets, really doesn't care if you pick the bubble sort, it's working like charm. And sometimes you need to pick the algorithm for the concrete problem to solve, because some algorithms it's better solving some problems. And of course, if you need to sort only the sequence of numbers, it really doesn't matter which type of algorithm you're picking. You need to look into time complexity then. And today we look into the Radix Sort, which is also it's made from counting sort or extended from counting sort. Also, you see that both sorting algorithms in the single implementation. And we also look into the bubble sort, and we look to merge sort. Other sorting algorithms really similar or same implementation you're able to see in the internet, and I will give you a link where you will find like visualization, and here you're able to look how it works, like if you needed to look how it works, selection sort, etc. It's really not a big deal to look if you would like to see how it works, like here. And other table, it's more maybe informative. When you see the same representation, you're always picking your algorithm first. You see the worst case. If you need a time, you look into the time complexity. If you need a memory, you look in the space complexity. And of course, if you're working with merge sort, it's not optimal to use if you need to save some space. It's more optimal using shell sort, bubble sort, binary search, it's searching algorithms, selection sort, insertion sort. And today we look into those three algorithms, and first I would like to show some pseudocode for bubble sort, and later we try to implement in the C++ language. And here I show the visual representation also from this website here. And when we move into bubble sort pseudocode, you will see that we have some you see here bubble sort array, we passing array, and here we have sequence or collection. We start from 1 to index last of unsorted element -1, and if left element is more than right element, we swapping those elements. And the bubble sort also known as exchange sort also, like we're changing the elements. And how it works in the graphical way, if you have example, here we have the A array like 7, 4, 5, and 2. First you have that array, you're picking two numbers, and 7, 4, and comparing both. If the first is more, you swapping that element. Then you're moving to the next two elements. Let's see here. 7 is more than 5. You swapping those elements. When you swapping these elements, you moving forward here and comparing those two numbers like 7 and 2. Is more or less. 7 is more, you swapping to the swapping elements. And after this first iteration or first step, you move to the step 2. You're picking, because you have the new array, it's like new unsorted array, and you just moving from the front, begin and swapping, not swapping, moving forward, 5, 2, swapping, okay, that's it. Now we're moving to the step 3, you just comparing those two numbers, swapping, and there is no swap, it's sorted array. And of course, if not swapping happens, you just moving forward and checking if you implement the algorithm, and it's not optimized way to use that. And how to optimize I show later. And complexity for a bubble sort, it's O(n), like power 2, and both worst and average case, because the entire arrays need to be iterated for every element. And for that case, you get the huge complexity line. And if you need to update or upgrade your bubble sort to optimized way, you have to add it swapped flag. And when you use this flag, if there is no swap left, you're able to ignore moving forward, because you don't need to swap again those elements, and you're not wasting the comparisons. And here is updated, upgraded, a bit optimized pseudocode. And first we would like to implement this bubble sort here. And when you're implementing the algorithms, we just able to create separate function, void bubble sort. And of course we need to have the array, and we need to have the array size or length. And later on we need to move for the whole array size -1, because we have here, as you see, index last of unsorted element -1. Here's pseudocode. That means you just have the concrete algorithm and you need to follow that pseudocode. And for we moving through the whole collection from the start to the last element -1. I less than n -1. And we need to update the counter or the i++ step. And later inside, because we not moving only the indeed, we need a column, because we're moving from here to here, and we need to move those two values, like we have the first and second. How you comparing? Yes, and if you need to compare those, you need to inner loop also. For and j equals 0, it's inner loop for the moving another element inside this array, and you just n minus I -1. And why you need this? Because you need the first element and second element to compare later. And j++, and here inside this loop we need to write the function main. Idea is to compare first array first column or first element in a column, and you comparing with this, like if more, you create a ascending order. If you change this comparison mark to a different way, like this, you will get descending then. Ascending, descending orders. And array j+1, because we need the next one element. First element and follows another element. And if it's true, you need to create a swap function. And how to create a swap function? First, you need to implement that. Easiest way to create a temp value inside here, but you're able to create a swap function outside, because best practice to have the functions separated from the basic block of code, because if you write a lot of spaghetti code inside a single function, it's really hard to understand later what is going on here. And swap function workings like to swap two elements. We need to create swap function. We take the pointer, doesn't matter x and any namings. It's like two elements, I and j, or x and y, and etc. And you need a temp value, like you're doing the same in that place if you're not separating this function. And here you need to make the first passed first element, and this element you would like to swapping out or to exchange, to change to agreg. It's like swapping operation here. Like x is now agreg, and if you would like to say that agreg is equals temp, it equals x at the moment, like swapping elements. X is now y, here y is equals x. You're just swapping out those elements. Temp value, it's only to hold the temporary when you swapping the elements. And here we enough to write the swap function and to pass the address of array j and array j plus 1, because we comparing those two elements. Sorry, because we need to change this array. And when you do like this, we need to print it out those and check that is work or not working, our bubble sort. And we able to create a function to display void display bubble sort. And to display, we need to iterate through the our array. For example, we able to create maybe display bubble sort, and we just picking the array, any array of elements like 66, 45, 20, 10, 9, 8, etc. We have the array, and we just would like to print it out first the array, cout unsorted array, and here we would like to for whole array and it's enchant loop for loop array. You're able to use as index % to save the memory. And here we would like to print it out our array, cout I. And of course we need some space between the elements. And here we printing unsorted array, and we need end line. And here we have the unsorted array, and of course we need the sorted array. I'm just copy the same function, and between that we need to call the bubble sort algorithm. Bubble sort and passing the array and passing the array size. Like how to count the array size, we need to calculate size equals size of function array, it's like whole array, and we dividing by single element of array. Single elements doesn't matter, first, second, or any. And we passing the size. And here we calculating size. And after this calling function, we just say that sorted array here. And or just we able to remove this end line and just we adding to this sentence. So okay, then we just showing the numbers after sorting here. Display bubble sort. Now we need to check is it working or not. Display bubble sort. Okay, we try to run it. As you see, bubble sort algorithm takes less than the output of bubble sort. It doesn't matter at the moment. And we get some output. As you see here, we get the 66, 45, 20, 10, 9, 8. We get 8, 9, 10, 20, 45, 66. It is working, as we see, and if you need descending order, you enough to change the switch operator here. Oh, sorry. Here. And you will get descending order here. And for your task 5, you need to create a ascending descending order. It's like able to use the bubble sort. Of course, able to use the already implemented in C++ default sorting algorithm using, but you're able to implement your own sorting algorithm. And here is like comparisons. I don't know, maybe we able to make some counter. Counter, is it possible? I'm not sure. Counter, and we just count the swaps. How many swaps happened here? Counter plus plus, and after this we just see out to console how many swaps happens and counter. Okay, try to open this. 0. Zero. Oh, because of this, maybe. Counter plus plus. Oh, sorry. Yeah. If are swapping counter plus plus. How we calculate here? Why it's 0? I don't know. At the moment, why it's 0? Four. Okay, we are here. Zero, zero, zero. Maybe before this. Okay, so for a moment. Doesn't matter how it I'm not sure why it's not working now. Maybe not a big deal here, because the optimization for this algorithm able to create a swap element, and for example you just create before the our inside loop we create and swapped equals 0, or you're able to create boolean, like boolean flag. Here is a flag, it's false, 0, and later if the swap is happening, you just make it here swapped equals 1. And after this you need to write like inside, if there is no swapping in the last swap, then the array is already sorted, and in the last swap it's like elements, you will break the loop, like you need to add here. Between here you adding the sentence if swapped equals 0, if swapping is not happening here, because you always have 0 if you're not making swapping operation like this, you just breaking our loop, because you don't need to do anything here. And here it's some optimization for the our bubble sort, and this fix helps a lot if you have a huge data set, because you don't need to swapping more. And also we need to look into another algorithm, and bubble sort, I think that you understood what the basic idea is. Like you have the two elements, like you need a double loop because you need to move through the column and comparing those two elements. And if it's more or less, doesn't matter which way you comparing, like ascending or descending, you just swapping those elements and you're moving again, and again. Like here you're moving, swapping, and you're just getting sorted array. And okay, now we're moving into the more interesting algorithm. And first you need to understand what is this merge sort doing here. And merge sort is a divide and conquer algorithm, because you know that recursion is the divide and conquer paradigm. Then the algorithm is divide and conquer using the recursion. And basic idea is breaking down into several sublists until each sublist consists of single element, and merging those sublists in the manner that results into sorted list. Like you dividing the huge problem into small parts, in the small sub-problems, and you solving the smaller problem. There's just only sublists, and in your sublists you're comparing only two elements, and it's much easier than create the, as you see in bubble sort, you need to iterate through the whole collection. Or here it's different way, it's like dividing it into a single element, and this element is as a single list, and you comparing those sublists and you get sorted array. And time complexity, list n is divided into max log n part of merging of sublist into single list, takes O n time, and the worst case run O n log n. It's better than the bubble sort, and as you know, as you understood, that here it takes a lot of memory. And why it takes a lot of memory? Because you need to divide in sublists, and those sublists, it's really memory usage. Increase the memory usage. How it looks in real algorithm implementation? You just have the big problem. Maybe add some marker here, and you have the first array. Your array is like from 8 elements. You're dividing or splitting by half, and first graph moves left, and then you move right, and you get the sublist. And you splitting that sublist in 2 parts, and you moving here, you just getting 4 sublist here, and in the right also 4. And when you're using the recursion, you will solve that two separate recursion calls. First for the left sublist, and second for the right part. And the main goal is to create that structure. First, you need to implement your algorithm, which is dividing that any type of collection into 2 small parts and more in 2 small parts, etc. You just creating some algorithm which is do like this. And another goal is to compare the elements. When you have only the single element, it's easier to compare between those 2 elements. Like if 7 is more than 3, you then swapping those elements like here. As you see arrow, and also you're comparing here with swapping, and you also need to make the function which is merging those results in the sublists or in huge, like backward compatibility. I don't know how to spell it. You have first you dividing, then you merging. That process is merge sort. That's why it's calling the merge sort. And when you're merging like sorted sublists, smaller sublists, and later you just moving here, and how it's sorting, you know that first element always is smaller, and you're comparing first element between that element. And maybe I'm just deleting this stuff, and we adding here. You comparing this element and this element, and 2 is less. Then move here, and 3 is more. Of course, move to the next part. Now we picking the 7 and 16. 7 is less. Okay, we just leave here, and the last element automatically added here. Here it's not so hard to understand. Yeah, first elements you're comparing, you merging, and here you just make it merge like this. And later when you have the huge Control C, we have the bigger sublist. You just comparing first element. First with that. Okay, you leave that 2. Now 3 with 4. You leave it 4. 7, 4. You just moving 4. 7, 9. 7 less, move here. 16, 9. You moving 9. 16, 11. You moving 11. 16, 24. You moving 16. And left 24, just adding 24. That's it. The whole idea is like to work like this. And of course, it's not so easy to implement. Of course, there is a lot of implementations already added in the internet. It's not hard to see how it works. But if you would like, I also recommend it to implement your own this algorithm to understand how it works, or try to update some code, like you look into internet implementation, or just try to implement your own using your thinking. Like, of course, you need to separate and merge in those elements. And how it looks into implementation, this one, maybe I will show you now. And I'm just moving to the C line. And we need to delete this, this stuff from here. And first, you need to create a function. I'm moving here, maybe I add more spaces here between. And we adding the function which is dividing and merging the elements. Because the main algorithm is using recursion, it's not so hard to move to the left and right side and divide into smaller sublists. And the hardest part is to implement a merge operation. We create a merge sort and merge function, like 2 functions to implement this merge sort. First, we need to create a merge operation or function, which takes our collection array, and we picking the our left. It's like L is equals start index of collection array, and we need the middle, int middle, middle, like you have some interval, yes, between that, for example 0, element 5, and here n. 0 is L, 5 is middle, n is last index. First index, last index, and middle index. Because we need to divide we need to split our collection. And R is right side, or the R is equals end. And now we need to create our some, I don't know how to call it, like temporary variables, and IJK. Later we need to use those for our different loops. I later, when explain, here it's I is initial index of first subarray, J initial index of second subarray, It's like left subarray, left, right subarray, and merge subarray. You need to have the 3 sublists. And now we need to calculate the range of the first range for the first subarray. We need m minus l and plus 1. And what is happening here? You just from the middle element removing the last, and you will get the first range of first sublist range or first subarray, because those subarrays later we using, like we have the subarray of 10 elements, of 4 elements, of 2 elements, and of 1 element, etc. And another subarray we have r minus m. It's like from left to right to the middle, and from the right to the middle. It's another subarray. And of course we need the subarrays, and left subarray is n1, and right subarray is n2. I write a subarray to understand what's going on here. And now we need to copy this data from the collection into those subarrays. Copy data to subarrays. The left subarray, you need to create a for loop, and I equals, we don't need I equals, we write I equals 0 and I less than 1, I plus plus. Because we need the first subarray, and left subarray, I equals left subarray equals array all plus 1. Okay, here we have the left subarray. Now we need to create the right subarray, and that equals 0, sorry, spelling, and 2, yet plus plus. Here we just create initializing right subarray. Yet equals array m plus I plus j. We have the our right subarray, and we just copy the data from the array. Doesn't matter which size of the array. We have the left subarray and right subarray. And we copied this data, and we need to take that I equals initial index equals 0 and k is equals l. Let's merge subarray. First subarray, second subarray, and merge subarray here l. And now we need to make our algorithm starts working, like to able to switching the order, but we need to looping the while our I less than n1 and j is less than 2. We just comparing our left subarray I is less or equal right subarray j. If this, we just creating our comparison here, ascending or descending. Ascending is when you're using the less equals, or descending when you're using the less equals or more equals symbols here for that comparison. And when you have the I less than n1 and j less than n2, you just making the some swaps, or not swaps, or you just merging some. Array k equals left subarray I, and you just increment the I here, and for that reason the while it start working here. And you just, when you're comparing, you just like we saw before, we comparing two elements of from the left subarray and right subarray, and you adding to the our array k, it's merge subarray and subarray I, and else we adding our array k, you will guess maybe it's right subarray, yes, right subarray, and here you get the element, and of course j++. And you just, as you see here, we comparing those two left and right, and our goal here, as you see, left and right, you here comparing, and if this number is less, you just taking from the left index, or how it's explained here, if this less in while loop, you taking from the left subarray element or from the right subarray element. That while it's for that purpose here, to sort our, to merge our subarrays and putting the element in the merge array, in merge subarray. I don't know how to explain. Array k sig is merged array. Okay, after this, if you have the situation when you not need to, like we saw before, when you have the situation when you comparing the 16 to 24, 16 adding here, and 24 left, or 16 left, doesn't matter, in left or right subarray left some elements, and not able to compare those elements. For that reason, you need to just put it into this array. And what you need to write here, and you need, of course, to delete this stuff. And you need to write to just copy this elements. If while condition I less than 1, if still elements exists here, you need just copy those elements. Array k equals left subarray I. You just copy your elements. If there are any elements left in this subarrays and you're not able to compare anymore, you just copy and add it to the merge subarray. And for that reason, you need to write 2 loops more. J less than n2, and now you need to write like array k equals right subarray. For that reason, you just copy, just copy these elements and get plus plus, and of course k plus plus. K is merge array, and here, as you know, that right array, and here left array. Left, right, okay, so here merge array. Here the basic idea is copy remaining elements to merge array. You're just copying those left elements. When you finish comparing, some elements exist, you just copy and adding to the merge array. Okay, and for the merge, for the dividing and merging part function is implemented, and now left the base algorithm to create like this here. The first step, like to divide into separate parts, separate parts, separate parts. We implemented that part to divide and merging, and maybe a bit those to divide and then merging, but we now implementing the basic functionality, and we saw what's doing here, and we need to write our other function or the basic algorithm, void merge sort. And doesn't matter if you're writing the more code, it doesn't mean like you're wasting more time to solve the problem. Of course, you get a better results, but you're wasting more memory. And merge sort, you need to pass the array, and we passing the two elements like int L and int R. Start and end of the array. And here are some problems because we implemented inside the function. So for that, we need to implement here, like merge sort. We must implement like this. If L or start left is less than R, or right index, we should to calculate or find our middle element. And to find middle element, it's either way. For the large data sets, there is two options. I'll able to write like L plus R divided by 2. First implementation. And if you have the huge data sets, it's not best way. Better way to implement the same stuff using the L plus R minus R divided by 2. It's as you see here is a more complex way, but doesn't mean it's not effective. Here is more effective way than you have different implementation, as I showed before. Like there is also implementation L plus R divided by 2. The same for calling the middle of element, but here is more effective way. And how to sort our first and second part, you need to call recursively merge sort, and you passing our array, and now we passing the left and middle. Left and middle, that range from left to the right. Left sub array, and we have the right sub array m plus 1 to the right. It's like from 0 to middle. Oh, here it's from middle, how to explain, middle plus 1 to the right and to the n. If you have like this representation like m and n, you just splitting for the left and right. And when you have this splits, you're calling your ranges. You also need to call the merge operation later when you merging these algorithms. You just passing array, and here you're passing L, M, and R. And that algorithms like splitting, as you see, till the single element and later merging those elements. And the basic algorithm is already implemented here. Only need to display our output. And Maybe we just copy this function, and later, of course, I will put this code into GitHub source control, be able to look into more details. And instead display bubble sort, we just display merge sort. Here we're calling merge sort. I'm not sure how to display at the moment. Merge sort, or should I call this merge sort? Maybe I'll look here. Tutorial. Merge sort mid end. How to print it out. This merge sort. Maybe it's range 0 from the size. Just try it. Display merge sort. Nope. Unsorted array, sorted array. It's Maybe there's some mistakes left here for output. Array lm, array m+1 r, merge array lmr if l are less than r, and we just creating array. Okay, and later we just creating the array. Left array 0. $66. Oh, it's that array is really doesn't help because it's really descending order. To create 10, 15. Then 20, 10, 9, 8. Okay, it's the same array. No, it's not all. It's not the array 0. I really forget how to use it, merge sort. For the output to the console. Okay, later maybe I will show, but the main idea is to how it's working. And start and end. Have the array, start is array 0 and end is array size. And so on. Run. Please run this program here. Stuck. No, it's not sorting. I don't know why. If we just copy this here, display merge sort, and later we just sorted array. No, it's not like this. Maybe I later added the output for merge sort. But the main idea how it works, it's functionality already implemented. But we need to print it out the merge array. And later maybe I appended here appending output. And to do later I will add it here in GitHub. And now the latest algorithm, we need to look into the Radix Sort, and here pseudocode. And Radix Sort, it's fast when the keys are short, for example when the range of array elements is less, and use suffix array construction algorithms like members algorithm and the C3. And there is some algorithm which is using this. Disadvantage of the Radix Sort depends on digits or letters. Radix Sort is much less flexible than the other sorts. Hence, for every different type of data, it needs to be rewritten. Because you need to rewrite for different types. The constant for Radix Sort is greater compared to the other sorting algorithm, and it takes more space compared to quicksort, which is in place sorting. The Radix Sort algorithm is an important sorting algorithm that is integral to suffix array construction algorithms. It's also useful for parallel machines. Basic idea, I will explain it fast, and we just tried how it works. Right example. Radix Sort, you have the sequence here, and the base idea, you just first taking the one digit or just one digit elements, like first digit 1, or if you have the 10, you take the 0. first digit from any number. Like if you have the 1, 2, 3, first you're picking the 3. And the idea is to add it into different classes. First class is zeros, 1s, 2s, 3s, 4, 5, 6, 7, 8, 9s. And we have the number 10 is first element, and we picking from the 10 the first element. It's like from one digit. And the first element of 10 is from the ones. If you get one digit, it's 0. You add it to the class 0. 21 is 1. You move to the class 1. 11 is here. 123 is 3. 644 here. Idea is classify into those groups by the one-digit numbers. Next step is to move to the other trash here. And second is 10 digits. Like when you're dividing by 10, you will get the first number, yes? Like 10 divided by 10, you get 1. Or when you're taking the number, now 10 digits, like when you have some 10 divided by 10 equals 1, or you just getting the first element. And now 10 is moves to the class first. Instead of this class, we're moving here. 10, 11, 17, 21, 123, because we taking this number, we taking this number, and we taking this number. In the 10 digits. Now moving more deeper, we're moving 100s. And in 100s, as you see, you just added some zeros between, because 10 dividing by 100, you will get 0, 10. And the first 100 number is 0, and those numbers which is already added here, moving to the first section. And 123 moves to that here, and 644 moves here. And now you just adding these elements already sorted here. That part, you just adding this number follows this number. And this sequence is already sorted. And our goal to implement this algorithm using the simple C++ language. And first we need to, of course, use the counting sort algorithm also to count that how many elements inside this buckets or classes, if the single elements already classified. And first we need to get maximum array. Function get the largest element from the array. Okay, we create the int getMax. Int array and int n size of array. We just looping, int max equals array 0 for int I equals 0 and not 0, from first I less than n I plus plus, And if array I is more than max, what's happening here? We returning max. Oh, sorry, max equals, we returning max equals array I, and here we returning max. Here is to get the largest element in the array. Now we need to implement counting sort algorithm. Void count sort. Or counting sort. And first we need the array, and array we need to int size, int place, and const int max equals 10. We have the table of 10 elements from 0 to 9, and output equals size and count 10, or sorry, count max output size, and now we just we're adding zeros to this. For int I count. I equals 0. Oh. Okay, in that we just adding I zeros. Now we calculate the elements. For int 0 I plus plus, we just adding counting elements. Count array I divided by place, mod 10 plus plus. It's really strange algebra here, but it's working. Able, of course, to separate those lines. Of course, you make from the single line like 4 lines or 7 lines. It's easier to write like this. Another 4. Okay, 4. And I equals 1. I max. I plus plus. Waits internet. I1, I max. Oh, here. Sorry, I don't understand what is going on here. Okay, we have like this, and now we need to calculate cumulative count. Calculate cumulative count. Here will be the calculate count of elements And here we count I equals count I minus 1. Okay, here we calculating, we don't need this brackets. Okay, we have like this, and now we place the elements in sorted order. The next step. Place elements in sorted order. And now we need to write like this: for and I equals size minus 1 more equals 0, I minus 1. And now we just output count. In count we adding some logic array I divided by place divided by place mod 10 and minus 1 equals array I, and count array I divide place mod 10 minus. Okay, it's really strange implementation, but it's working. And now we need to add it to array I for and I equals 0, I less than size plus here are the basic steps. Array I equals output I. That's it. Okay, here is a counting sort, and this counting sort, it's not so hard, but first you need to try to implement your own. And here, of course, we're able to remove some lines maybe to make it more readable. And the basic algorithm left here, you need only the two functions. Void radix sort, because the radix sort, it's using the counting sort algorithm. It's for that reason you need to implement different sorting algorithm and later to use that functionality in radix sort, and radix sort is really not so huge to implement. It's only upgraded algorithm of counting sort. Int array, and here we need int size or n, doesn't matter. And first we need to max element, get max array size. Okay, array, and we need the size. And now we placing to the elements and using for loop. For in place equals 1, max divided by place more than 0, and we just leaving the place or step more than equals 10. And in for loop we just calling our counting sort, passing the array, passing the size, passing the place. And that's it for our radix sort. Now we just creating an image of simple array, like with numbers 5, 15, 24, 40, 62, 25, 59. That's it. And we just calling our counting sort. Oh, sorry, not counting sort, Radix Sort. Radix Sort, we pass in the array, and we pass in the size. Okay, size of array, white, size of array 0. And we just printing out our array. I'm just copy from here that. Okay, I'm copying here and printing here. Sorted. Maybe that one it works now. And array. Okay, let's try to print it out. Yeah, it's working now, fine. And for merge sort, maybe I fix and add it to output for merge sort. Here, as you see, you have this not sorted array, and here you see the sorted array using the Radix Sort. And as you see, those algorithms really different in some strange options. There is different ways to implement, but those algorithms need to compare, and some usages of all algorithms, it was in different algorithms also. And I think for today is enough, and thank you for your attention, and please try to look into this web page which I added also here. Here it's maybe more explanation. If you need visualizer here, just run it and testing with your how to visualize how it works. How counting array, as you see here, you counting the elements, and here we this aux array sorting now our elements. And for that lecture, that's it. Thank you for attention, and if you have any questions, we able to discuss in the next section, next lecture, and I will add also this code into our course, and I'm just maybe share now this project on the Git. And in the video down below you will find, or in Moodle also, I will put this implementation of code also. And okay, thank you for attention. See ya after the first programming course ends.